Applied mathematical programming. Hypothalamus artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its solutions for startup real-world problems. The growth of mathematical programming will not stop. The problems that can be solved every day, making use of computational power, will be greater every day, which for now will not stop. Just as the complexity of the problems grows, so will the mathematical intelligence of the human being, which has not stopped growing. The first step in learning any science usually, but not always, takes place in academia. There, the student learns methodologies and technologies, using very small, one could say toy, application cases, too far removed from the applications required by the real world. In praxis, complementary knowledge is generated, whose application cases are increasingly distant from the toy models of academia, due to the super-accelerated growth of information technologies, which little by little break the barriers of dimensionality, leading to a change in the paradigm of applied mathematics that has gone from sequential computing to parallel computing. In this video series, Hy presents some of his experiences, surprises, which have helped him learn to deal with very complex problems, up to the creation of artificial entrepreneurial brains. Applied mathematical programming. The first lesson that praxis gives is that the models applied differ quite a bit from the academic ones taught in theory. For example, a fundamental methodology for mathematical modeling, relational information systems, is often left out. Without a good knowledge of SQL, it is impossible to create the databases that real industrial systems require to be optimized. Next, some typical problems of praxis will be presented, the solution of which becomes a new mathematical problem. Applied prescriptive artificial intelligence. Unfeasible primal solution. A non-expert practitioner does not visualize the importance of this problem, perhaps because he has never experienced it. An unfeasible problem is due to poor formulation, or the content of databases, which for small problems can be easily solved, but for large and real problems, the situation is very different, and it is usually a headache. Identifying that a problem has a feasible solution may be trivial, but identifying the reasons for the non-feasibility can be very complicated. To facilitate this process, a good database, which complies with integrity, is the only way, since, without complying with integrity, it is not possible to run the mathematical model. Additionally, when the database is apparently fine, it may be necessary to include in the mathematical formulation, sets, or parameters, that help detect the primal infeasibility. Feasibility and Infeasibility and Optimization is a timely expository book that summarizes the state of the art in both classical and recent algorithms related to feasibility and infeasibility and optimization, with a focus on practical methods. All model formats are covered, including linear, nonlinear, and mixed integer programs. Connections to related work in constraint programming are shown. It is a broad topic that must be studied, if we want to solve real problems of great dimensionality. In some problems, a feasible solution is already known. In others, finding a workable solution may be the hardest part of the problem. An optimal solution is a feasible solution in which the target function reaches its maximum, or minimum, value, for example, the greatest benefit or the lowest cost. A problem has optimality conditions, which are related to Lagrange conditions, and feasibility conditions that are related to the constraints of the problem. In some algorithms, these two aspects must be considered, which can be moved sequentially or simultaneously. An irreducible infeasible subsystem, IS, is a method alloy used in optimization to analyze non-feasibility and solve the feasibility problem. An IS is a minimum set of constraints and variable limits that is not feasible but becomes feasible if one, or any constraints, or bounds, are removed or correct and solve the problem. ISes are used to identify the constraints and variables bounds that make a problem unfeasible. Once identified, these restrictions can be removed or corrected to make the problem viable. An infeasible problem may have multiple ISes. In this case, the optimization problem will need to be adjusted multiple times to make it feasible. Problems calculating an IS may be because the model is not bound or has numerical problems. It is a broad topic that must be studied, if we want to solve real problems of great dimensionality. The traditional way of attacking the problem of feasibility and optimality is in two consecutive stages. We look for feasibility first, and then optimality. The standard process is to solve the original monolithic model, using an optimization algorithm appropriate to the format of the problem. This focuses on the use of algorithms from commercial houses, such as IBM Plex, Gurobi, Express, that have tools to identify the ISAs group. Based on its experience, HI has developed its own methodologies for IS management. The first method is based on the classic two-phase optimization. To do this, the phase 1 model must be generated, which involves relaxing all or part of the restrictions. In the case of constraints, this involves including a relaxation error for each constraint and substituting the objective function for a sum of errors, which can be linear or quadratic. If the optimal solution is equal to 0, the problem has a feasible solution. In case of feasibility, in the second phase optimality is sought and the problem is solved. The image presents an example of the setting of a constraint for phase 1. The parameter f_relax controls the two passes. When it is equal to 1, the process is in phase 1. f_relax equal to 0 indicates that the process is in phase 2. Divide and conquer is a strategy that involves breaking down a complex problem into smaller, easier to solve subproblems, and then combining the solutions of these subproblems to get the solution to the original problem. This strategy is applied both in the resolution of computational problems and in political and military strategy. Divide, split the original problem into multiple subproblems until the smallest subproblem is reached. Conquer, from the smallest subproblem, the solution to the original problem is built, merging from the bottom up, the solutions of the subproblems. The optimization process is organized sequentially in such a way as to facilitate and accelerate the obtaining of a feasible initial solution. The idea is to carry out the optimization process in n steps, in which the first n1 are related to the check for infeasibilities and the last with optimality. HI has proven, in the real world, the effectiveness of this method. Soft constraints, penalized for their violation, can hide hard feasibility issues, since, depending on the cost of the penalizations, it is impossible to differentiate a feasibility error from the activation of the artificial variables related to the violation of soft restrictions. Splitting the process into 3 phases avoids this problem. Considering the complexity, for the initiation of a combinatorial problem, HI has frequently used the divide and conquer strategy. A problem that must be faced is the feasibility of hard restrictions, in which case the source of the infeasibility must be identified and corrected. 2 sources of infeasibility must be considered: mathematical model with errors in its formulation, and errors in model data. HI's experience taught that trying to prove the unfeasibility of a monolithic problem can take an unreasonable amount of time. Therefore, a version of the model was built that would allow the feasibility analysis to be carried out efficiently and quickly. To conquer, the model is divided into subproblems that can be solved, sequentially or in parallel. In the final stage, the subproblems are merged to obtain the feasible or unfeasible solution. This process will always be faster and use less memory, possibly solving non-solvable problems in a monolithic way. Problems are the result of the modeler's experience. Lack of industrial database quality. It is one of the problems of any database that is going to be used as input to a math model. A relational database, RDBMS, is a way to store and organize data in tables, rows, and columns to establish relationships between data points. Relational databases are the right way to read data for mathematical models. The first step in processing a model is to read the information system and load the database into memory with all the parameters read, basic to the model. These parameters will be preprocessed, generating secondary parameters, to complement the database. All parameters are converted into inputs for the optimization model. The results, post-processed, will be stored in the database. Data validation procedures have 3 stages: input data, calculated data, and input data ready for the run. The screen shows SQL connectivity to the database in an IBM OPL program. The screenshot shows access to all master tables in an education system. And the secondary ones store the relationships between entities. The screenshot features the master table of the classrooms, and the following secondary tables. Classroom, sections, classroom, classroom types classroom, restricted hours, and multimodal classroom, single classroom. The first problem that the modeler faces is the construction of the database. As the database grows, typical of real systems, they get bigger and bigger, due to the computer power. Database errors lead to mathematical problems in model execution that can be complex to solve. The most well-known problems due to integrity and/or truthfulness errors are feasible solutions reported as optimal, which do not correspond to the true optimal solution, unfeasible solutions, and unbounded solutions. For large systems, it is essential to have informatic tools that guarantee the data quality. The following issues must be resolved: validate the mathematical formulation of the model, database integrity, empty sets, feasibility analysis, and non-bounding analysis. Any of the above issues can coexist in the same database. Another source of problems is related to the existence of empty sets once the pre-processing of the information has been carried out. These sets can lead to unfeasible solutions, or to suboptimal results that do not consider all the resources available in the system. An empty set is not by definition an error, but in certain cases it corresponds to an error in the data or gives rise to runs that could hide errors. The modeler's role is to determine the actions to take when an empty set is found. It's not a mistake and it doesn't affect the run. It is a data error, and the execution must be aborted, or it is an anomalous situation that must be reviewed and reported, but it does not stop the run. These are some of these cases. An empty set for the matters that a professor can teach. This situation indicates that the teacher should not be part of the run, or teachers who can teach the matter, but who, due to lack of data, do not appear in the database. Empty set for teachers who can teach a matter. This situation leads to the impossibility of meeting the demand for enrollment in this matter, which implies that the matter should not be part of the run, or there are teachers who can teach the matter, but due to lack of data in the database do not appear. Therefore, for each set incorporated in the mathematical modeling, the action to be taken when this situation arises must be indicated. This does not guarantee that the data are correct but facilitates the process of verifying its quality. Data management implies that secure procedures must be implemented to reduce data issues. Therefore, the following verification processes should be implemented. Data integrity and veracity rules in the data model to be transferred directly to the servers. Calculation processes that automatically generate data from other data, to avoid manual procedures that generate errors. It is part of the pre-processing of optimization processes and usually needs to be built as part of the model. Precise validation rules for calculated sets and parameters, to check empty sets and out-of-range parameters. This will speed up the implementation of the math model. Validating the information increases the reliability of the model. These database problems may seem easy to solve, which is true when the case is academic or a toy model. But it must be considered that, if the system is real, the size of the database requires powerful tools. Finding the defect using a monolithic version of the model that works with a high-performance commercial solver is no guarantee of success. In a discrete model of the real world, due to its highly combinatorial nature, to prove that there is no feasible solution, it is possible to have to explore the entire combinatorial space, consuming solution times that tend to infinity. HI's overall focus is to develop specialized procedures that significantly reduce the time to find non-feasibility issues and significantly decrease time to solution. In a traditional method, feasibility is handled in 3 stages. The feasibility of hard constraints is obtained, soft restrictions are activated, and optimization process is executed. If the feasibility for the hard constraints is not obtained, the process may be stopped. The process implemented by HI divides the stage of achieving hard feasibility into multiple optimization subproblems, whose solution must be feasible to guarantee the feasibility of the monolithic problem. Independent subproblems can be solved in parallel, subproblems that are linked must be solved sequentially. Accelerating to get to the feasible starting point. Real cases. Case: Cement Express, modeling cement production. Accelerating to get to the feasible starting point in mixed nonlinear mathematical programming. Cement production lines are associated with a mix of continuous and discrete processes, and nonlinear material blending processes. If a detailed simulation of the entire chain is desired, a highly complex model of mixed nonlinear mathematical programming must be faced, which is briefly analyzed. The image presents the energy consumption throughout the process, which is divided into electric power in the milling of raw materials, thermal and chemical energy in the furnace, and electric power in the cement mill. The production of pollutant emissions is concentrated in the clinker furnace. Mixing processes ensure product quality and operating conditions. The blending along the process is raw materials plus correctors, fuels, and clinker plus additional. The transformation process may be divided into three parts, which give rise to three mathematical models: raw grinding, oven, and cement mill. The simulation of the linear furnace must be carried out in detail, in the order of meters. This is because the chemical process that converts clinker paste to clinker takes place throughout the furnace, and the temperature of the furnace must be kept in sync with the chemical energy produced by the materials involved in the chemical composition of the clinker paste, along with the thermal energy of the combustion of the fuels. The chemical process is developed from the temperature of the furnace, which varies along its axis. In this way it is possible to calculate all the material flows that are produced, including pollutant emissions. In this way, the consumption of thermal energy, the composition of the clinker paste, and the production of pollutants are combined. Fuel blending is necessary to minimize heat generation costs, while respecting emission control. Raw grinding, oven, and cement mill. Trying to get an initial solution, or proving the unfeasibility, of the monolithic version of the model, was impossible for High by using realistically sized systems and testing various algorithms to solve mill problems. The strategy followed to solve the problem that seemed insoluble was, divide and conquer. The monolithic model was divided into three problems: raw grinding, kiln and cement mill. These subproblems are solved sequentially, and at the end of each stage they are joined with the next subproblem, until the model is integrated, as if it were monolithic. Case: School Express. Timetabling model. This case, taken from the client's application, presents variations made to solve the real problem, simplifying the optimization process. School timetabling modeling. The academic timetabling focused on course scheduling usually corresponds to the curriculum-based course problem, in which the set of subjects is predefined by a curriculum that determines a series of subjects that the student must take, and the allocation of resources must comply with certain business rules. CBCTT includes periods, courses, teachers, curriculum, and classrooms. The CBCTT is aimed at achieving the best assignment of the classes of the course to the rooms and periods, satisfying the following physical limitations. Master classes. All master classes in a course must be scheduled, and must be assigned to different periods. Room occupancy. Each room can accommodate a maximum of one conference per period. Conflicts. Master classes of subjects belonging to the same curriculum, or taught by the same teacher, cannot be scheduled in the same period. Availability. Periods not available to the course teacher cannot be used to schedule a masterclass for that course. The goal is the minimization of the weighted sum, according to given weights, of multiple objective functions, representing the costs for the violation of the following soft constraints, business rules. Minimum number of working days. For each course, a penalty is given for each day below the minimum number of working days. Curriculum compactness. In some cases, it is preferable that the lectures of a curriculum are consecutive, without any empty period in between. Thus, a penalty is given for each isolated lecture. For example, a lecture not adjacent to any other lecture of the same curriculum in the same day. Room capacity, a penalty is given for each student that cannot have a seat in the room assigned to the course lecture. Room stability, it is preferable that a course is always taught in the same room, thus, a penalty is given for each additional room used for a course. In addition, or in replacement of, some of, the soft constraints other cost components may be considered. Windows, student min-max load, travel distance, room suitability, and double lectures. All the entities that are part of the CCT are related to each other, and they visualize themselves connected through relationships between them. In this case, grades, sections and courses. Matters and resources. Teachers' timetables, matters by teacher, subjects and sections. Spaces, subjects, time and sections. It should be considered that each of the above relationships defines an individual subproblem that must be feasible for the integrated model to be feasible. Therefore, an alternative to test feasibility is to divide the model into many small subproblems and test the feasibility of each of them individually, which will be much more effective than testing feasibility in an integrated way. All data must be stored in a relational database. The screen is an example of the master table of matters and its relationships. The result is the timetables for all the relationships of entities that are part of the system. All timetables are expressed in terms of binary variables, and therefore it is a high-dimensional NP-hard problem. Again, the strategy followed in the feasibility analysis was divide and conquer. The success of the strategy was total, without it would have been impossible to meet High's commercial commitment. The screen presents the declaration of the artificial variables of the constraints in a GAMS problem. The screen shows the objective function for the feasibility analysis. The solution report identifies the constraints that could not be met. The modeler should not forget that this constraint may be one of the irreducible and infeasible subsystems. The GAMS program presents declarations of the subproblems included in the model. The GAMS program presents the sequential execution of the divide and conquer process. Optex's ability to handle multi-problem models makes it easy to set up models and problems by reducing the process to a fill-in-the-blanks process. The screen presents connectivity of problem, subproblems and constraints in Optex, optimization expert system. The table presents the summary of the planning of 17 schools carried out by High. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Thank you for your attention.